we are discussing the force convection inside pipes in the lectures. Uh, just let me recap that what we have discussed yesterday. So we discussed about laminar flow in tubes or pipes. So in this we determined about the velocity profile and in terms because we know that if we do the differential analysis for a pipe flow, and we know that the velocity profile for a pipe is usually parabolic, and if we know the distribution of velocity, that is parabolic, which is given by this equation. So as I told you in the last class, that this derivation is done in this section a dash I think a dash 5. So we just because we know that in from our fluid mechanics course that this 8-39, if you look at the relation, that v of r is minus r upon 4 mu dp by dx 1 minus r square upon r. So uh, we just integrate it from 0 to r to get the value of Vm. So from where this formula came, because we derived this formula, Vm is equal to 2 upon r square 0 to r Vr dr. And if we do that, we can see that velocity distribution is 2 Vm into 1 minus r square upon capital R square. So r is small r is a variable which is 0 at the central line, and it is equal to r at the pipe surface. So from here we can write the velocity in terms of pressure drop, and then pressure drop can be related with the mean velocity by this relation. And then we know that Darcy friction factor can be related with the pressure drop by this relation. So then again here it should be rho, not mu. And then in the last class we also seen that we can write the uh, power required for that pump to make that happen at a volume flow rate v dot, that would be equal to uh, pi d raised to power 4 into delta p 128 mu l. So this is volume flow rate, and then uh, we can determine the pumping power from here. So we discussed this thing, and then we did this numerical problem that if we want to know the pumping power for a particular case, then how can we determine that? So is there any query from this, from the last lecture? So if there is no query, we can continue with the discussion, because we have only discussed the pressure drop and the pumping power. But for the case of heat transfer, we need to determine the Nusselt number correlation, right? So let me take you back to the book. So in order to determine the Nusselt number profile, we again do the differential analysis. So if you look at this figure, that here we have got a circular disc type differential element whose thickness is dx, and the energy which is coming into this element, that is m dot cpti, and the energy going out is m dot cptx tx plus dx. And then because the heat is going out, you can see qr is at the inner surface and qr plus dr is at the outer surface of the this type ring type differential element, and the thickness of this element in the radial direction, it is dr. So if we apply the energy in is equal to energy out, then we can write m dot cp ti, which is energy in the axial direction, plus q dot. So here the q dot r is coming into that element, so that's why it is plus. And then there are two minus terms, which are the energies going out in the axial direction and radial direction. So from here, if we do a little bit of mathematical manipulation, like if, instead of m dot, we can write rho rho v into 2 pi r dr, and then if we apply the limits here for an infinite extremely small element, for that we can write it in this differential form. And from here, if we do the integration bit, not the integration, but it is just the, here we have done what we have done here, that we have written it in terms of uh, pressure, this temperature gradient, and we have also got the temperature gradient in the radial direction and the temperature gradient in the x direction, right? So now this equation 8-53, what does it tell us? That the rate of net energy transfer to the control volume by mass flow is equal to the net rate of heat conduction in the radial direction. So if we look at this element here, so physically it says that whatever heat is coming in the axial direction, that net rate, which is the difference between these two, would be equal to the net rate which is going in the radial direction. So whatever there is a difference in heat transfer in the axial direction, that would be equal to the uh, rate of heat transfer in the radial direction, and that we can appreciate that, because if that is a steady state flow, so whatever heat is coming in the axial direction, that should be going uh, out in the radial direction. Now from here, from 8-53, we need to determine that what is the value of temperature as a function of R. So for that we can use the knowledge, because for the constant heat flux case, we know that partial T by partial X is equal to 2 q dot s rho vm cp into R. So from where I have written this formula, if you know that on the whiteboard, we did the derivation in the last class. I think it was somewhere here. Yes, 2q dot s rho vm cp into R. So if you look at the table, at the book, they have shown the same thing. So in 8-53, we can replace partial t by partial x with this 2q dot s divided by rho vm cp into R. And then what else we can do here? That for the Vr, we know the relation. What is the relation of Vr? That is, we have derived in yesterday's class. So that is also, if you look here, Vr is equal to 2Vm into 1 minus R square upon capital R square. So if we put these two relations here in equation 8-53, instead of Vr, we put Vm into this 2Vm into 1 minus R square upon uh, capital R square, and instead of dp by dx, we dp by dx, which is sorry, partial t by partial x, we put 2qs upon rho vm cp into R. So if we do that, and then here we have done that, so then the left hand side, it is written in terms of qs and this term. And then now if we want to determine t of r from here, then we can integrate it in the radial direction. So because that is a second order differential equation, so we need to integrate twice. So in the first, after the integration, C1R plus C2 would come there, because it is a indefinite integral. And then if we put the boundary condition, T is equal to T, first of all, at the center of the pipe, we would have symmetry boundary condition, which we also discussed in chapter number 3. And then at the pipe surface, we have got T is equal to Ts at R is equal to R. So if we do that, we come to equation 8-57. So now you can see that T of R is equal to T of S minus Q dot S upon K R into 3 by 4 minus R square upon R, capital R square plus R raised to power 4 divided by 4 R raised to power 4. So what does it tell us? That the temperature in the radial direction that depends upon the surface temperature and the flux value of that, and also the K value for the fluid. This term in the bracket, that is due to mathematical manipulation. So the main thing here is temperature depends upon the surface temperature, the flux which is coming in, and the radius of the pipe, and the thermal conductivity of the fluid. So let me take you back to the lecture slide now. So I have written this relation here. Uh, so I skipped that all derivation bit because it is just the mathematical aspect of derivation. So we are more interested. Of course, we can do that derivation at our own time, but what we are more interested in is the physical aspect of this relation. So which I have explained, that T of R depends upon these four parameters, and if we want to calculate T of M from here, which is the mean temperature, so in the first lecture, if you remember, in the introduction, we also derived one relation for Tm, which is mean temperature. So it was equal to T of M was equal to 2 divided by Vm R square T temperature profile, velocity profile into R into dr. So now we are going to get Tm value, which is the mean temperature from this derivation. Any question up till here? Because I just shown you the derivation on in the book, which I had skipped in my lecture slides, so you can go through this. But you can do this derivation, and you can definitely derive these equations on paper. But I suppose that it is not very difficult to do it. And secondly, the main thing is that how we can determine Tm from this A-57. So that is what we are going to do. So velocity profile we have written, temperature profile we have written here. Now the mean temperature is 2 upon Vm R square T of R into V of R into R dr. So for the fully developed thermally fully developed flow, the x dependence wouldn't be there. There would be only dependence upon radial direction. So if we put these values here and do the integration, and then if we simplify, we can get Tm is equal to Ts minus 11 divided by 24 q dot s r upon k. Okay, so from here we can, if we have got this relation, let me just then we have got whiteboard. So if we see, so we have got Tm is equal to Ts minus 11 by 24 q dot s upon rk. So from here, if we want to calculate qs in terms of what would be the qs value if we want to calculate, that would be equal to q dot s would be equal to Tm minus Ts into 24 by 11 into k divided by r. Now we also know from our Newton's law of cooling that heat flux is equal to H into Tm minus Ts, right? If we are talking about the cooling of the fluid. So for the cooling of the fluid, because the heat is going away from the fluid to the solid pipe, so we can write it like this. From uh, oh, sorry, it is other way down. Let me write it again. I think I have made an error here. It should be Ts minus Tm, and then here it would also be Ts minus Tm. So if we compare these two relations, we can say that it is the same thing. And then we have got Qs here, the same flux. So from here we can say that H value is equal to 24 by 11 K upon R, right? So if we write it uh, in terms of diameter, then it would be equal to 48 by 11 K upon D, right? Because R is equal to D by 2, and 2 would go into the uh, numerator, and then it would be 48. And now if we want to calculate Nusselt number from here, Nusselt number formula is H D upon K. So if we put the values here, instead of H, we are putting 48 by 11 K upon D upon K. So it would be cancelled, and Nusselt number becomes equal to 48 by 11, and I think if we simplify it, it would be something 4.32 or something like this. So it means that Nusselt number is constant in, in laminar steady fully developed flow, and its value is 4.32 for constant heat flux boundary condition. So it means that we are talking about laminar steady flow on which we have got some flux coming on this on its surface, right? So for this value is important, and that we can also know from our discussion in the yesterday's lecture or the previous lecture, when we said that if we plot h as a function of x, then we can say that if this is the entrance region, so in the entrance region h value decreased, and then it became constant value. So if h is a constant value in the, this is fully developed, and this is entrance region. So in entrance region it decreases because h is basically partial. It was k into partial t by partial y minus k into it was ts minus tn. So partial t by partial r, not partial y in this case. So let me correct it. It should be partial r at r is equal to capital R, which is the pipe surface we are talking about. So because partial t by partial r is constant in the fully developed flow, so that's why this whole thing is becomes constant. So that's why Nusselt number is also constant value. Now that is something which we have derived. So Nusselt number here it is equal to 4.36, and then if we do the similar kind of derivation for the Nusselt number for the constant surface temperature boundary condition. So this derivation was for the constant heat flux boundary condition, and it was if we do the similar step for the uh, constant surface temperature boundary condition, Nusselt number becomes equal. Again, it is a constant value which is 3.66. Yes. Any query? Anything you want to ask? Okay. So now thermal conductivity K for so it means that uh, we have got thermal conductivity K for use in the Nusselt number should be arithmetic mean of the mean temperature at the inlet and outlet. So that's okay. So Nusselt number is not dependent upon the friction factor for the laminar flow, but for the turbulent flow, it is always dependent upon the friction factor, which we would see in the next week's lecture. And then if you see that here we have written 3.66, 4.36 for the constant heat flux boundary condition, and then friction factor is 64 divided by Reynolds number, which we calculated in which we discussed in yesterday's class. So similarly, we can get the Nusselt number correlation for the Nusselt number values for different kind of cross section like ellipse, triangular, rectangular, and here the first column is second column is for constant temperature boundary condition, third column is for constant heat flux boundary condition, and the last column is the friction factor which is required. So we can do this. So if we know the cross section and we know the its geometrical aspect ratio A divided by B, then we can easily see the value of Nusselt number. And once we get the Nusselt number, we can calculate H uh, from there for the laminar flow. Okay, and then if we are this discussion was only limited to the fully developed region. So in the entrance region, if it is an entrance region for a circular tube of length L, subjected to constant surface temperature, the average Nusselt number becomes, because now you can see that 3.66 plus something, because if we go here, I had told you that in the entrance region, Nusselt number value should be greater than the fully developed values. So if we are talking about constant surface temperature boundary condition, so it is 3.66 here, Nusselt number. So in the entrance region, it should be greater than that. So that value they have shown it on the here 3.66 plus this value. And then if we want to know, if we want to include the effect of that viscosity difference at the surface of the pipe and the bulk mean, which is the arithmetic mean of viscosity at the inlet and outlet, then we can include it in the relation, which is again all these relations are empirical correlation for the entrance region. And then for the isothermal parallel plates, so for that if we want to know the Nusselt number, then we haven't discussed, we only discussed about the pipe here, but here if we have got two parallel isothermal plates, then we can get the Nusselt number for that by using this. And you can see here DH, that is hydraulic diameter, which is 4 into cross sectional area divided by perimeter. right? So this is something which we have discussed. So I think we can do the numerical problem in uh, in next class for this. So you would be doing one uh, quiz, quiz number 4. Maybe it would come at 10 per 4 on your screen. So uh, just wait for another 2 minutes. So it would be there. So then we can see it. Is there any query from today's lecture?
No, sir.